Hello guys, welcome back to another lecture in this course. In this video, we shall be looking into Singular Value Decomposition or SVD. So we are going to look into the mathematical calculation or the mathematical computation behind the Singular Value Decomposition. And it is a matrix factorization technique that decomposes a matrix into a three matrix. It is widely used in various applications such as data compression, image processing, recommendation systems, and many other applications. So the SVD or the singular value decomposition factorizes a matrix. For example, it can factorize a matrix M of different size given M by N dimension. So it only factorizes it into three matrices, and these three matrices is of U, summation or sigma, and V power T, where we are saying here our matrix, for example, matrix given M is equals to U multiplied by the sigma or summation. So this sigma we are multiplying by our V power T, where M is representing our original matrix, which is given original matrix. And remember, this original matrix is of size M by N, depending, and we reduce it to a 3 matrix of this value. And also U here, it is denoting a orthogonal. It is just denoting a orthogonal matrix of M by M. Obviously here we are just saying U is representing the left singular vectors of our matrix, which is M. And the sigma in this manner, our sigma or our summation, this let us call it sigma or summation. So this sigma, it is only representing the diagonal matrix. So this represents the diagonal matrix of the same size, remember, of size M by N. And lastly, we have V power T, which is nothing but our transposition or the transpose of the matrix. This one is the transpose of and it will be of our orthogonal matrix. Orthogonal matrix V here of size, it will be of size N by N. In this manner, we are saying the transpose of this matrix, it is nothing but just the columns. This is the columns of V, where are these are just the right singular, let us say the right singular vectors of our original matrix M. So as you can see here, we are just saying in a singular value decomposition, we are taking a matrix that we are having, either it is having 4 rows, 5 columns, or whatever, 10 rows, 10 columns, but we are decomposing the matrix into 3 matrices, where we are having U by sigma by our transposition of the matrix, as we are seeing here, as I explained each in this section. So now we can see that now the singular value decomposition, it allows us to express a matrix of A as a combination of singular vectors and singular values. Let us take a look into a mathematical problem solving of a singular matrix decomposition. So what we can do, let us find the singular. So we are creating a question. Let us find the singular value decomposition. Singular value decomposition. Let us find of a 2 by 2 matrix. So, assuming we are having a 2 by 2 matrix with the components -4, let us say -7, 1, and 4 here. This is our matrix. So to do singular value decomposition, the first step that we should do, let's say first step is to find the transposition of the, we need to find the transposition of the matrix. To find our transposition of our given matrix, we are going to say A power T is equals to, so this is our matrix. So we take this value and this value. We're going to do matrix transposition. So it will be -4, -7 here. And also same applies here. It will be 1 here, 4. So this is called transposition. After doing a transposition here, we need to multiply the matrix here, the first matrix, and its transposition. So to do so, we are saying T power T is equals to our original matrix -4, -7, 1, and 4 dot our transposition matrix, which is -4, -7, 1, and 4. So we are going to multiply these. So -4, which is nothing but 16, plus -7 times -7, which is 49. And also 1 times -4, we get -4. Then 4 times -7, we get -28. Same applies, we are saying -4 times 1, we get -4, plus also we are saying -4 times -7 times 4, it is nothing but -28 here. So here we are also getting 1 plus 16 here, 4 times 4. So now we need to add. So after adding this, 16 plus 49, we get 65. And also -4 minus 28, it is nothing but 32. And also -4 plus -28, it's -32 again. Then here we get 17. Right. So this is another step. Now another step here, let us call it our second step. Let's find the eigenvalues and the eigenvectors of our transposition matrix of our AAT. So all this we are decomposing, we are looking for the singular value, we are doing our singular value decomposition. So to do so now, let us start by finding the eigenvalue. Let us start with eigenvalue. So to find the eigenvalue, obviously we use the determinant of our matrix minus lambda and identity matrix equals to 0. So here it will be, our A dot A, our transposition matrix minus lambda identity equal to 0. Therefore, we are saying now bracket 65, so it's 65 minus 32 and 17. So here we are saying 65 minus 32 minus 32, 17 here, okay, which is our transpose matrix, our matrix here, minus lambda identity matrix 1 0 0 1 equal to 0. And if we are to add this, to subtract this, to multiply this with the identity matrix, we get our identity matrix here 32, negative 32, 17. So if we multiply with a scalar, it means with a scalar lambda, we get lambda 0 0 lambda here equals to 0. After doing so, we are computing 65 minus lambda minus 32 minus 32, 17 minus lambda, all equal to 0. So we just say 65 minus lambda, 17 minus lambda. As you can see, we get the identity matrix of this. We get this matrix. So after getting this matrix, what we need to do now, we need to find the determinant here. Let's see, find the solution using determinant concept. So here we are going to use the determinant concept where we are multiplying this times this times this. So we subtract again. So we are saying 65 minus lambda times 17 minus lambda minus 32 times minus 32, all equal to 0. Now 65 times 17, which is nothing but 1105, minus 65 minus lambda, which is 65, minus 65 lambda, minus lambda times 17, minus lambda times 17, which is nothing but 17, negative 17 lambda. Negative lambda times negative lambda is a positive lambda square. Negative 32 times negative 32, which is nothing but negative 1024 equals to 0. So negative 32 times negative 32, we get 1024, which is a positive number, minus this for determining, minus operator here. So what we need to do now, we need to collect like terms. 1105 minus 1024 minus 65 minus 17, we get a negative 82 lambda plus lambda square, which is equals to 0. 1105 minus 1024, we get 81 minus 82 lambda plus lambda square equals to 0. So now, as you can see, we are having a quadratic equation. Okay, so I prefer normally to solve using factorization method. Factorization method by splitting the middle term. So I'm going to use splitting the middle term. So if we are using splitting the middle term, This is 81. If you multiply these two here and here, you get 81 lambda square. So only two numbers that we can get, and which gives us negative 82 here. It's minus 81 lambda times negative lambda to give us 81 lambda square. With this same number, negative 1 lambda plus negative lambda, we get a negative 82 lambda. So what we can do, we use these values, minus 81 and minus 1, to split this middle term. So here we are saying 81 minus 81 lambda minus lambda plus lambda square equal to 0. Now let us factorize 81, then 1 minus lambda. We factor out negative lambda, which gives us 1 minus lambda, which is nothing but 0 here. Now what we can do, we can write our polynomial as 81 minus lambda, 1 minus lambda, all equal to 0. So now we can form an equation where 81 minus lambda is equals to 0, or 1 minus lambda is equals to 0. Therefore, we are saying for a scalar, minus lambda is equals to minus 81, in which we are dividing with a negative 1. Divide here by a negative 1. We cancel this, and we cancel also this. Lambda become equals to 81. Or lambda here, our scalar, is equals to negative 1. We divide by negative 1 all over negative 1. We cancel this. We cancel this. Lambda is equals to 1. So here we can see now that our eigenvalues of our matrix AAT are the scalars which are 81 and the lambda equals to 1. Now, since now we have get the eigenvalues, now let us find the eigenvectors. We need to find the eigenvectors for each and every eigenvalue here. So let us start with equals to 81. Let us start with lambda equals to 81 to find its vectors. So to find its vectors, we just simply use this formula, T minus our lambda identity matrix. But here now you multiply with our vector 1. Okay, so vector 1, or we can call it x1, so that we can form a simultaneous equation. Okay, so now let us make a substitution. So we substitute values here. In this case, we are saying on our matrix AA here it's 65 minus 32 minus 32 and 17. That's our AAT, minus our identity matrix, which is scalar 0, 0, scalar or lambda here, times. So times our vector 1. We are looking for the vectors, eigenvectors. So since we are looking for the eigenvectors, we can put v1, or let us use x1, all equal to 0. So all these are multiplied by the vector, because here, remember, I say v1 or x1. This is representing our eigenvectors. So it's 65 minus lambda minus 32 minus 32, 17 minus lambda. Here, all multiplied by x1 or our vector 1. Since we are substituting lambda is equals to 81. So we are saying 65 minus 81 minus 32 minus 32 and also 17 minus 81 here. All multiplied by our vector 1 equals to 0. So this will give us 65 minus 18, we get a negative 16, minus 32, minus 32, 17 minus 81, we get a negative 64 here. All multiplied by our v1, which is x1 here. Now, what we need to do now, let us multiply with the x1. Okay, so if you multiply with the x1, what we get negative 16 x1, okay, minus 32 x here. So instead of writing x1 on this one, let us write x2 since it is on the second column. So, and also minus 32 x1. This, let us call it minus 64 x2. So what we are going to do here, what we are implying here, we are going to create a simultaneous equation just like we do in mathematics. So our simultaneous equation will be 16x1 minus 32x2, which is equals to 0. And same applies minus 32x1 minus 64x2 is equals to 0. So here, if we are to subtract, let us subtract here. If you are to subtract minus 16 minus this number, it means we get a positive 16, 1. Minus 32 minus this number, we get a positive 32x2 here, which is equals to 0. After getting this, we can divide by 16 here. And we cancel this and this, and we get x1 plus 2 x2, which is equals to 0. And by checking value 1, so it means this is our vector 1 value and our vector 2 value. So we can actually see that x1 is equals to, if this value goes to the other side, we can say x1 is equals to minus 2, and x2 here is equals to 1. So we can see that now our vector 1 is equals to minus 2 and 1. And if we are to look at our another lambda, which is lambda 1, we just apply our same concept where 65 minus lambda minus 32 and minus 32, 17 minus lambda here, and we multiply with our vector 2, which is equals to 0. So what we can do now, we can say 65 minus 1 minus 32 minus 32 and 17 minus 1. And all this times our vector 2 equal 0. Now this one is 64 minus 32 minus 32 and 16 times vector 2 equals to 0. And if we are to substitute, it means we get, if we are to substitute our values, we get 64, let's say x1 minus 32, x2 equals to 0, and minus 32 x1 plus 16 x2 for our vector 2. And in this manner, it means here what we can do is to add. And if we are adding these two, it means we get 32 x1, 64 minus 32 here, minus 32 plus 16, we get a negative 16 x2, which is equals to 0. And if we are to divide both by 16, we get nothing but 2x1 minus x2 equals to 0. So here we can actually see that x2 is equals to a positive 2, and also x1 is equals to 1, as you can see. So it means our second vector, which is vector 2, is having points 2 and 1. So these are our eigenvectors. So we are just simply say for eigenvector minus 2 and 1 in the length, with the length L, it means is equals to minus 2 square plus 1 square, which is nothing but square root of 5, which gives us 2.36. So in order for us now to normalize our singular matrix value, to normalize it here, we are saying V1 is equals to minus 2 over root 5 and 1 over root 5, which is nothing but minus 0.894, and other values are 0.447. And this is simply done by saying this. For example, we are saying vector 2 is equals to given values x and y. We are just simply saying it is equals to x coordinate all over the magnitude of the x coordinate. And also for the y value, same applies, and it's the magnitude of the y value. This is the normalization for our singular value decomposition math. So now for eigenvectors of 2 and 1, so after commuting, we are saying that L is equals to the magnitude of 2 square plus 1, which is equals to root 5, which gives us nothing but 2.236. So now to normalize our value, we are saying to normalize, it gives let us call this V1. Let us say this is V1. These are values for V1. Now we need to normalize for V2. And V2 points equal to 2 and root 5 and 1 over root 5, which gives us positive values 0.8 0.894 and 0.447, the positive value. So now, to conclude our lesson, using these values now, we can write the solution. We can write the solution now as, for example, of our matrix M equals to U by our sigma, and our transposition matrix, we can write it this way. Sigma here is equals to our, now we are saying root 1, 0, 0, the matrix 1, root 1, which gives us nothing but 9, 0, and 0, 1. And also, we were saying that U, it is representing our vectors 1 and vector 2. So, since it's representing vector 1 and vector 2, we are saying our vector 1, 8, which is negative 8 and 4, and 0 and it is 0 and 4, 0 and 4, 4, 7. And positive 0.894 as well as 0.447. Or if you want to represent it in square root, you can say negative 2 root 5 and 1 over root 5. Here 2 root 5. Here is 1 over root 5. So I think this is all for singular value decomposition. So this last step that you can see, this is the decomposition concept of matrices. I think this is all for this lesson. Thank you for watching. Bye bye.